Good morning, students. Mr. Carver here. Today, we are going to be doing inverse trig functions, and we're going to be deriving them. All right, so let's start off by talking about what we need to do in this section. I would like you to memorize these 6 formulas. The first, if you derive with respect to x the arc sine of u, what you get is 1 over the square root of 1 minus u squared times u prime. Now, the reason I'm using u's is because u is a differentiable function of x. If you just have an x here, this will turn out to be 1. However, if this is something other than just x, this will then be the derivative of it. So this covers us for every potentiality using the chain rule. All right, now I'd like to pause here just for a second and show you where this comes from. I'm not going to work through all 6 of them, but just so you get an idea of why this derivative is the way it is. All right, so let's start out by talking about letting y rather be the arc sine of x. And if you remember, arc functions, as I said in a previous video, arc functions, or inverse functions rather, are angles. So y is the angle, that is not a question, and x is the ratio. Now, assuming that x is positive, I'm going to draw a triangle in quadrant 1, and I'm going to let this angle right here be y. Now, if the ratio is just x, remember it's the ratio of 2 sides. This is really x over 1. That is opposite over hypotenuse. So that means this side is x and this side is 1. All right, since this is a right triangle here, I can use the Pythagorean theorem to solve for that adjacent side right there. And that turns out to be the square root of 1 minus x squared. All right, now if I take that y function and I sine both sides, the sine and the arc sine will cancel each other, and I end up with this. The sine of y is equal to x. So I'm just putting it back into normal form when you first started out trig last year. And then the reason I'm doing that is because I can now derive both sides using the techniques that I already know. I don't need to use the derivative for the arc sine. That's what I'm trying to show you. So the left-hand side, if I implicitly derive with respect to x, I'm going to use the chain rule. That's going to give me the cosine of y times dy over dx. That would be really 1 times dy dx. And on the right-hand side, I get 1. Now, solving for dy dx gives me 1 divided by the cosine of y. And remember, y is an angle. Again, not a question. So what I'm going to do now is I'm going to take out this expression right here, and I'm going to substitute it with the actual ratio of the cosine of y based on that triangle. So here we go. My dy over dx then is equal to 1 over the cosine of y, according to that triangle, is adjacent over hypotenuse. That is the square root of 1 minus x squared, of course, times 1, which is the derivative of what I was arc sining originally. So you can see how I get this equation right here, or this, yes, the equation giving me the derivative of the arc sine. I can take this, and I can jump straight to there using that formula. That is 1 over the square root of 1 minus what I am arc sining squared. Let me put parentheses around here, maybe to make this a little more obvious. So I'm arc sining x, that is what I'm arc sining squared, times the derivative of what I'm arc sining. In this case, it's just 1. Now, you got to be careful. This part out here is just the derivative of what I'm arc sining. Again, that's just x. Don't derive the x squared or the 1 minus x squared quantity. All right, so that shows you where that comes from. Let me give you the other 5, and then we can work through a few problems. All right, so the derivative of the arc cosine of u turns out to be negative 1 over the square root of 1 minus u squared times u prime. Now, the nice thing about these 6 is the sine and the arc cosine, the arc sine and the arc cosine are exactly the same, except the derivative of the arc cosine is negative 1. Now, if you recall back from chapter 2, I did mention that anytime you derive a trig function, that is a cofunction, that is, a trig function that starts with the letters C and O, will always have a negative derivative. That continues to be the case in section 5.8. So sine is positive, cosine is negative. All right, so the next one then is the derivative with respect to x of the arctan of u. And this turns out to be 1 over 1 plus u squared times u prime. And then, of course, I think it would make sense that the derivative with respect to x of the arc cotangent of u will be negative 1 over 1 plus what I'm arc cotangenting squared times the derivative of what I am arc cotangenting. All right, two more. The derivative with respect to x of the arc secant of u turns out to be 1 over the absolute value of u times the square root of u squared minus 1 times u prime. All right, just as you might have thought. And then lastly, the derivative with respect to x of the arc cosecant of u. That turns out to be negative 1 over the absolute value of u, square root of u squared minus 1 times u prime. All right, now a couple of things. I know as you're working through this, this all starts to kind of look alike, especially the first line and the third line, right? The arcsine and the arcsecant. So a couple of things I just want to point out. Order is very important when you are subtracting. So the arcsine has 1 minus u squared, whereas the arcsecant has u squared minus 1. The way I keep this straight is arcsecant also has this absolute value of u outside rather, and those u's are then magnetized, bringing them together, which makes the u squared come first in the arcsecant. I don't know, it's just something that kind of helps me keep those straight. All right. Now, there are typically a few students who always ask about this last line right there, the arcsecant and the arccosecant, why that actually has an absolute value in it. I'll do that toward the end of this video. If you'd like to watch it, just stay tuned. I'll give you a warning before I start it so you can sign out if you have no interest in it. All right, so let's work a few of these problems. All right, let's start off with an easy one, the arcsine of root x. When I derive that, I get y prime is equal to, we just start using the formulas from the previous page. Upper left there, that is 1 over the square root, 1 minus u squared times u prime. All right, here we go. This is 1 over the square root of 1 minus what I am arcsining, the quantity squared, times the derivative of what I am arcsining, that is 1/2 x to the negative 1/2. I will let you know if I need you to clean these up. This is actually fairly easy to clean up. This will be y prime is equal to 1 over, I'll put the 2 out front. This is the square root of 1 minus root x squared, just gives me x. And I also have another root x out front. So 1 over 2 root x times the square root of 1 minus x is simplified enough. And that is your derivative or your slope machine for your original y point machine. All right, now you have to be careful here. You got the arctan of 3x, everything being squared. The negative 1 on the tan is not actually an exponent. It's a notation for the arctangent. So I can't take negative 1 and multiply it by 2. That is a no-no. I know it's super confusing. They should have come up with another sort of notation, in my opinion, but it is what it is. We got to work with it. All right, so I'm forced to use the chain rule twice. I've got something raised to the second power. We will start there. So my y prime is equal to 2 down front. I've got the arctan then of 3x to the first power. Keep track of what I'm deriving as I derive it. And now I go inside and derive the arctan. This is 1 over, I don't want to write it in red, I want to write it in black. That's 1 over 1 plus what I'm arctangenting squared times the derivative of what I'm arctangenting. Now I've taken care of that. And I've also taken care of that, because remember, the arctan formulas that I gave you covers you for the chain rule derivative of the arctan. So that 3 is the derivative of the innermost function. All right, and this is where you'd leave it. I'm changing my mind. Actually, let's go ahead and just clean this up here just a little bit. So this is going to be 6 arctan of 3x over 1 plus 9x squared. The simplification that I gave you is not going to be super difficult. Anything that has a very complex derivative, I will just have you set it up only, but this is your slope machine for your original y. And speaking of which, I might give you something like this. How about y is equal to the natural log of x squared minus 1 times the arc secant of 5x. All right, so now what you're noticing here is that they're going to mix in the new formulas with all of the old formulas, even going back as far as chapter 2. In this case, the product rule. All right, so here we go. I've got y prime then is equal to the derivative of the first. The natural log of x squared minus 1 goes to 1 over x squared minus 1 times 2x. I'll take that times the second one as is, underived. And then I want to multiply that by, not multiply, I want to add it to then the reverse, right? So the first is the natural log of x squared minus 1. And now I'm going to derive the arc secant. That's 1 over the absolute value of 5x. It's supposed to be an absolute value sign, times the square root of 5x, the quantity squared, minus 1. I'll go ahead and put the 5 on the top. I'll extend this over, and I'm going to get rid of this. And I'll put that back, just to save a little bit of room. All right, so this would be something that's super complex. I don't want you to take any time cleaning this up or getting a common denominator or things like that. You can just leave it just like that. Incidentally, I did mention that if you have bases other than e, you can use that formula regardless of what the base is. So the natural log does have a base of e. You could also put in 1 over ln of e. Remember, it's 1 over the natural log of the base times 1 over what you're logging times the derivative of what you're logging. This, of course, comes from the Department of Redundancy department. You don't really need that, right? 1 over ln of e is just 1 over 1, which is just 1 after I carry the 1. All right. All right, so that should be enough to get you through tonight's homework. Guys, I'm going to go ahead and show you where that absolute value comes from. So if you're interested, keep it playing. Otherwise, you can stop and get after it, all right? So hang on just one sec. All right, so this goes back to earlier in this section, right, when we're talking about arc functions. By the way, this is not drawn to scale. It is an absolutely horrible drawing. But remember the secant curve. And by the way, we are talking about y is equal to the arc secant of x. Secant curve has a helper curve of the cosine, so that's what I've got here in gray. That's the cosine curve. Those are vertical asymptotes. Wherever the cosine is equal to 0, you have an undefined function. So then my secant curve, the part that is 1 to 1 goes from here up, getting closer and closer to that vertical asymptote, and from that valley there down, which is why it has a range and a domain written the way it is written in either original form, that is the secant of x, or the arc secant of x. Now this is a graph of y is equal to the secant of x. Now, if I find the inverse of this function, which will be this right here, the arc secant of x, remember it is a reflection over the line y equals x. It's very difficult to kind of show you this, but if I just take the red portion and I reflect it over the y equals x, remember what happens. The x's become y's, the y's become x's, and you get a drawing that looks like this. All right. This is really hard to visualize unless you actually sketch it on a piece of paper and then flip it over that blue dotted line there. But you actually get the arc secant of x looking something like that. And what you'll notice here is that, remember, the derivative of the arc secant gives you the slope of this arc secant graph. That is this graph in the green box here. And what you'll notice here is no matter where you're at on the arc secant of x, as long as you're in the domain of the arc secant of x, you have positive slope, which is why you need the absolute value, excuse me, the absolute value on the x. Now, let me get rid of the original secant graph here, just make some room for myself. And let's take an example where I might have something like y is equal to the arc secant of negative x. Well, if you recall from pre-calculus and in trig, that negative there divides all the x's by -1 on this graph in this box here, which flips it over the y-axis. Which means, without me sketching it, I'm not sure if you can visualize this, but it will be decreasing everywhere. It'll be going downhill everywhere we go. So if I go ahead and drive this using my formula, I've got a y prime is equal to, this is 1 over the absolute value of negative x times the square root of negative x, the quantity squared minus 1, times the derivative of the innermost function, which is -1. It's going downhill everywhere, so the slope must be negative. If this were not absolute valued, the negatives would cancel, giving you a positive uphill slope. The absolute value makes sure that the sign of the slope always works. I hope that works for you. All right, guys, that should be enough to get you through it. Thanks for your attention. Thanks for your hard work. I appreciate it. I will talk with you soon.